So, quick example. So let's think about the region that's enclosed by two semicircles. I want you to say that the radius is 2 and 1. Okay, so the previous inner circle is not so nice. Okay, so this is the region that we want. Yeah, let me change the color to be red. So this is the region that we want. So you can say this is the outer semicircle enclosed. This region is enclosed by the two semicircles and the horizontal line segments. So here, that's the region. Happy. Okay. So the outer is x squared plus y squared equals 4. We have the radius 2. And we have the inner to be x squared plus y squared equals 1. Okay, so this region, when we are writing the things, you can try to imagine that this is definitely not easy if you want to describe everything in terms of dx dy or dy dx, right? Description of this region D under dx dy or dy dx can be complicated. Of course, you can still do it, but then it definitely involves multiple pieces. For instance, let's say if you do the dx dy, that tells you what? That tells you y is free, and we're using horizontal bars. So at this point, you see you need a lower bound and upper bound, right? For x, right? But then if you go below this line, then you will have two pieces. And then you have you have two lower bounds and two upper bounds. That's two distinct line segments. And above the line, you will have a whole piece of line segment. Okay, so the thing just gets a little bit messy. And of course, if you try to imagine dx dy, then x is free, but then you will have different cases. Okay? So this is something that is really messy to deal with if you just play with dx dy or dy dx. Okay? So, so before we describe this region in terms of polar coordinates, let's quickly do a review. Polar coordinates. So the polar coordinates, the essential idea is that instead of doing xy coordinates, we describe by the distance from the points to the origin and the angle that's cut between the ray and the x-axis. Okay. So we call in the two-dimensional plane, xy plane. And suppose you want to describe a point, cap P. So here, if you do xy coordinates, this is the condition. That's just saying my horizontal coordinate is x, and my vertical coordinate is y. Right? So basically, so in the first quadrant, you can say, okay, x is how much you walk from the origin to that point along the x direction, and y is how much you have to walk vertically up, right? But then, if you want to write the r theta polar coordinates, then r is the distance from the origin to the point. Okay, so here you can see you form a right triangle, right? And R is the hypotenuse. And then theta is what? Theta is, okay, so here we established that you can say this is a OP, which is a vector, right? So basically you have you have the direction OP, you have the direction from along the x-axis. So there must be a rotation angle that goes from the x direction to that OP direction. Okay. So this is the angle theta. So here we can establish a few quantities that r squared equals to x squared plus y squared. So that's the Pythagorean theorem. So this is the way that you calculate the distance r. And then you also know that x equals r cosine theta, y equals r sine theta. These are trig identities about the coordinates. So basically from the right triangle. So sine theta is r over, y over r, and the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse, right? So, so this is basically the way that you relate between the Cartesian and the polar coordinates. But then here we like to quickly mention that note that this is something you have seen from Calc II, I believe. The choice of r and theta may not be unique. So firstly, here I want to mention that although we define this r to be the distance from O to P, but that means you tend to give positive values, right? But then it's also legal if you just use the negative distance, right? Because the positive is just saying, okay, for along the direction OP, I'm just going on a positive number of units, right? But then I can say, okay, I can go if I choose the opposite direction. Let me quickly draw that. So let me just draw the opposite point along the same way. So here, for this point, I can say, without changing the radius, I can say this rotation angle is different. Okay, theta plus pi. So that's the rotation angle from x-axis to the dashed line, right? So here I can describe this point to be r theta plus pi. And then now here this point, if I flipped the distance to be negative r, then what do I get? I exactly get the point back. Okay, I exactly get p back. So let me write that down for p. Okay. So this point can be described as negative r theta plus pi. So basically, what does it mean? It means, okay, if I decide this is the direction that I'm going along, then I change the distance from r to negative r. I'll go to the negative side of the ray. Okay. Basically, what this just tells you, okay, if you just increase the theta, increase the angle by pi, you are going to the negative side. And then if you change the sign of your distance, you get that point back. So that's exactly what it does. And of course, if you just add 2 pi, that's definitely going to give you the same point, right? So here for polar coordinates, this is something you have seen that you want to carefully decide the range of r and theta. So that's going to be also important when we decide the region for double intervals. Okay. All right. Any questions so far? So the key here is one is the distance, the other is the rotation angle. Okay. And of course, the angle theta, you want to pick a small enough range to cover every case and without taking multiple possibilities for the distribution. So example, so we'll do several quick examples. Of course, if you think about the unit circle, of course, the unit disk. So the unit circle is easy, right? But we are describing the regions. Okay. So this is the boundary is x squared plus y squared equals to 1. Okay. So here for this region B, we can see that so for the theta, for that angle, it definitely covers from 0 to it's one period, right? From 0 to 2 pi, let's say. But then we know that the distance from any point within the disk to the origin is bounded by upper bounded by y, right? So we can describe it by d equals to xy pair. Excuse me. Of course, this is not the xy pair anymore. It's r theta pair, where my theta is free between 0 and 2 pi. And so I just pick one period, and then so it covers every direction within the xy plane only once. And r is between 0 and 1. Right? So the upper bound of the distance is 1. And we make sure that the distances are positive. So it's good. Right, now let's look at the example that we had for the motivation of the section. So let me also cheat again by copying the picture down. So what happens if we have this kind of cut ring? So we see from the picture that firstly the angle theta. Okay, so there's a minimum which is the x-axis direction. Okay, and then when theta, so that's then you can say theta is 0 here. And then when it increases, and there's upper limit, right? So the maximum possible within the period from 0 to 2 pi is ending at pi. Okay. So here, if I want to write the r theta pair, so theta is now cut between 0 and pi. Okay, so that only covers the upper half plane. Right? But then it's kind of obvious in a sense that the distance is between 1 and 2. Okay, so it must be larger than 1, but less than 2. Okay. So here, r is between 1 and 2. So it's good. So here we can see that for this region, we have a nice, you can say this is kind of like a rectangle in the polar coordinates, in the sense that r and theta, they are both cut between constants. Okay? Let's look at another one. So yeah, let me quickly give you the figure, and we will talk about the details next time. So we have a circle that is centered at the point 1, 1, 0. And the diameter is the x-axis. So this the boundary here is x minus 1 squared plus y squared equals 1. So that's it. We're talking about the description of this kind of disk. Okay, but here the center of this circle is not at the origin, so it's slightly different. But we know that okay, the diameter here is on the x-axis. Okay. So basically, when we are trying to describe this region, so if you do xy, the xy variables, then you have to do some kind of a radical. So here, if you do polar coordinates, then so let's still draw the. Now we're going to draw the x-axis. Well, the x-axis will represent that the axis that's going through the origin horizontally, but then yeah, let me move it to the right. Because in the polar coordinates, we only have the origin and one direction, okay? And that's the x direction. And then we have a circle. So that's the circle that's included in the disk. Okay. Here, what we know here is that the center is this location 1, and the diameter is 2. So now, firstly, although if you are sweeping using the rays going through the origin like these, okay, and then you will see that the distance from the origin to the furthest point is going to be changing, okay. But then you can think about firstly we can think about the range of the angle theta, okay. So this rotation indeed is most negative value, which is negative pi over 2. Okay? And of course, is the opposite side is the most positive angle, which is pi over 2. Okay? So we can specify that range first. So here we don't really have the vertical axis in the picture, but that still represents the most negative theta value. So this is theta equals to negative pi over 2. And here this is theta equals to pi over 2. Okay. And now, in general, if you just draw a ray going through the origin, so this is the angle theta, okay? And then we want to determine, okay, what's the length of this adjacent edge of the triangle, okay? So we know, okay, so this angle right here is facing the diameter of the circle, so that tells you this is pi over 2, okay? So this is the right triangle. So we are looking at the adjacent edge. And also we know that the hypotenuse is diameter, okay, which has a length 2. That tells you what? It tells you this adjacent edge, so let's call this point P. So the distance from the origin to P, so this vector OP has a magnitude of what? Of 2 cosine theta, right? So this tells you, okay, so this radius, well, this distance from P to, and let me put it in right. So the distance from P to the origin O, this distance R is exactly 2 cosine theta. Okay. So now when you try to describe this region in terms of the polar coordinates, you can see that theta is cut between negative pi over 2 and pi over 2, but then R is cut between 0 and 2 cosine. So let's write it down. So of course, if you describe it in terms of the xy variables, then this is the disk, okay, which is enclosed by the outside circle, but it's in r and theta. So here we decide theta first, okay, because theta, we don't really have variables bounds. We don't have varying bounds, let's say. So theta is cut between negative pi over 2 and pi over 2, okay? It's because of the rotation that you can get for these rays going out of the origin, right? But then R has to cover everything on the everything on this adjacent edge of the triangle, right? So R has to be upper bounded by 0, lower bound, lower bounded by 0, upper bounded by 3 cosine theta. Okay, so you can see in this situation we have a varying R bound. Okay. And here, so any questions so far? So here, let me quickly mention. So this is not the only way to get the full description of the disk right here. So another way to think about it is that this disk, if you simplify this, this is actually gonna give you x squared plus y squared that's equal to 2x. So basically what you do is you multiply the square out, it's gonna be x squared minus 2x plus 1, right? And then on the right hand side you have less than equal to 1. Then you cancel the ones and then move 2x on the right hand side. And then you can say, okay, I want to substitute. So x squared plus y squared, if you translate everything in terms of r and theta, it's going to be r squared. Yeah, let me just write the equivalent arrows. R squared, that's equal to, okay, so 2, x is what x is r cosine theta. So this is actually a quadratic inequality, so that solves the range underneath. We do have a question. Yeah, let me do examples. Right, so there's always various ways to describe probabilities. Right, so any questions? All right, so here we have the descriptions of these regions using polar coordinates. Here comes the question. Suppose that a polar rectangle R is basically the region, but it's in terms of r and theta such that we have a specific fixed bound for the radius r, and also we have another bound for the angle theta. Okay, so these are fixed constant bounds. So that's a polar rectangle. How do we compute? How to compute the double integral over this region of a function f of x, y. Yeah. Okay. So basically, we have a region R like this, and then we have a function in terms of x and y. Okay, and then we are just accumulating it multiplying the way that you subdivide the region R. Okay, so this dA is still the way that you subdivide the base. Right, so here we see f of x, y, so it's natural that we translate everything in terms of r and theta. So we know that x is our cosine theta, we just substitute. Our y is our sine theta. We do that also systematically. Okay, so that's actually a critical step, right? And then here you see in the region we have r and theta. R and theta are between two specific intervals, so we can do the substitution here as well. But then a very important question is the following. So dA is going to be different because earlier when we were doing this actual rectangles, we are doing dx dy, right? But then when you subdivide a polar rectangle, then the way that you subdivide the region, the small increment of errors is going to be slightly different. Here, I'm going to quickly give the answer, and we will give you the derivation right after that. So, answer. So basically, like we mentioned, when you put down the intervals, you can say, let's say theta is on the outside, so it's from alpha to beta, and then that's for theta, and then A to B is for R. And then here, the function that we're accumulating is exactly the substitutions, cosine theta, sine theta, just replacing the xy values. But then for dA, it's r dr d theta. Okay. So still theta is on the outside, r is on the inside, but we have an extra r. We have an extra r here. And like that. Okay, so this r, the reason we have this r is because of the way that we subdivide a polar rectangle. Okay, or you can say it's a circular section. So let's quickly look at that. Recall. So when we define this double integrals right here, if we actually have a rectangle in terms of x and y, then what we do is we subdivide the rectangle in equal pieces, right? So that's the Riemann sum strategy. So we are going to do that once again. So whenever we have an integral that we want to define, we just do Riemann sum. So like we mentioned, if you have an xy plane and you have a rectangle in terms of x and y, then you just have a fixed range for x from, let's say, from A to B, a fixed range for y, that's from C to D, right? And then what we have done earlier is that we subdivide the interval from A to B into, let's say, n pieces. They don't really have to be equal, but the number of them just increase all the way to infinity, and the width just gets to 0, right? And of course, you can do equal pieces or non-equal pieces for the range of y as well. But either way, so the tiny little piece, the subdivision is a rectangle. Okay, so if you recall, we represent delta A the way that we subdivide to be delta x times delta y. Okay, the increment in x and the increment in y will multiply. Let's represent the area of a triangle. Excuse me, the rectangle right here. Okay. So this region we have the width dx and length delta x and delta y. Okay. So Here I want to now move to the polar coordinates. And it's a little bit different. So we are still trying to describe a region, but then, so the Cartesian plane is the xy plane, right? But then if you have the range in terms of r and theta, theta is actually giving you two rays, right? We have starting one that's alpha, and then we have the ending one that's a larger radius, so that's angle beta, right? So that's a little bit different. And now we have r from A to B. Okay, so r is actually the radius. So actually you have a smaller radius and you have a larger radius. Okay, so this is r equal to A, and this is r equal to B. Okay, so that's the region, which is the rectangle in the polar sense. Okay, so the rectangle in the polar sense, if you look at this, this is actually what's called a circular section. Right? But then now, if you want to do the Riemann sum kind of subdivision, so of course we have the interval from A to B. That's for r. We divide it up into equal pieces. Okay, so let's say 4 pieces. Then what do we do? So we can just do these arcs that are circular, right? So they have the specific different radii, right? And then we also subdivide the theta angle from alpha to beta, this interval, into equal pieces. Let's say 3 pieces. Then we have this ray going through the origin, and this ray, okay, going through the origin. So now you can see that each subdivision is also a circular section, right? So the two sides right here, they are along the same two different rays, but then these are the curves that are circular, right? Right. So now the dA is a little bit different from the left-hand side, because now if you think about it, we have the r and the theta, where the theta is the small increment in the angle. Okay, so that gives you an angle like these. Okay, so that's delta theta, right? And then when you talk about delta r, that's going to be the increment in the radius. So that from the smaller radius to the larger radius, right? So you have the region like this. So this is delta r, right? So here our question is following. So we want to look for the area of the subdivision right here. Okay. And the region is exactly the region that's enclosed by the two rays and the circular curves. Okay. So how do we calculate or how do we estimate this surrounded region? Okay. So that area is it has to relate to the radius. Okay. So the actual radius. So if you think about it, so you can say, okay, this region, it has a fixed width, right? So delta r is the width. So it's the same everywhere. Okay, if you just draw these rays out starting from the origin, right? So that's a fixed number. Okay, that's a fixed width. But then you can say, as long as we can estimate this arc, the length of the arc, then we just use this as the width of the rectangle, right? Multiplied by the the length of the rectangle multiplied by the width of the rectangle. Okay, so this multiplied by this. Okay, so that's an estimation. So and then how do we calculate the inner arc length? So if you think about it, it relates to the inner radius of the circular curve. So this is a radius r, and then we have the angle theta. So this arc is actually what? It's actually the radius times, and let me write it down here. So this is r delta theta. Okay, so basically the length of the arc that's facing the angle is that angle multiplying by the radius, the inner radius. Okay. Right. So here, treating the region as a rectangle. So actually, if you think about it, if your delta r is small, so if you have the inner arc like this, and the width is small, so the outer arc is almost having the same length, then you can just use the length of the inner arc to multiply by the width, right? Delta r. So this is our delta theta, right? So that's similar to a rectangular region. Okay. So we just use these to multiply. And delta A in this situation is our delta theta, which is the length of the arc times the width of the arc. Okay. And if you rearrange the order, this is just going to be r delta r delta theta. Right. So now we do have a description for this the area of the subregion, right? The subdivision, and then when we write down the integral, we just replace delta by d, right? So this is exactly why we have r dr theta. So hence, we can put things down. So when we talk about the double integral over the region R, it's a polar rectangle, right? Here we know this dA exactly is r dr d theta. Basically, we just do that with replacement of delta into d, and then we can rewrite everything all together. So theta is between alpha and beta, okay, d theta. And then r is between a and b, dr. But we just recall that we have to have that r here. Okay, very important. So this is so the double integral is written and dA is translated. So we just need to also fill out the functional expression. So x is r cosine theta, and y is r sine theta. Okay. So that's everything that we need to do. So let me here change the color into red. R is very important. Okay. All right. So so basically you can see that I would say the critical part for the double integral over the polar coordinates is this this part in red. Okay, so this r dr d theta, this is the important thing. Okay. So when we had dx dy, that's the tiny little width times the tiny little length of the rectangle of a small rectangle. So that's direct multiplication. But here, since let's look back at the figure. So you see, this region right here. So if you think about the one that's to the upper right corner, you can say, I'm looking at this one. Okay. So this one, it also is facing the same increment of the angle, right? It's delta theta, right? It's delta theta. And in fact, the increment of the radius is almost the same thing. So, but definitely the one on the right has a larger area if you just look at it, right? So this definitely relates to the distance from the region to the origin. Okay, so exactly that's the radius. So you can see that's also another indication that gives you the importance of this radius r right here. Okay. That's very important. Make sure you keep that in mind. All right, so now let's look at the example. So here we want to find the volume of solid bounded by z equals to x squared plus y squared and z equals to 2 minus the square root of x squared plus y squared. All right, so here I want to mention that if you see sum of squares, and especially if you see sum of squares under the radical, it's sort of like a hint that you probably want to use the polar coordinates. Yeah. So, but here, let's see, we have z equals to x squared plus y squared. This is actually a paraboloid. Okay, so basically this is a paraboloid opening upwards. If you want to do an illustration, that's something like this. Okay. Z equals to x squared plus y squared. Okay. But now, if you look at z equals to 2 minus the square root of x squared plus y squared, this is actually a cone. But it's opening downward. Okay. So you can see that the output is always less than equal to 2. Doesn't look so great, but okay, so like this. Okay, that's good enough. So here you can see that actually basically when you're doing cross sections, if you fix the z value, you can see that you will always get a circle, right? And at the same time, so you can see here the maximum z value is 2, right? And then let's say when x is, or excuse me, when z is 0, this cross section is actually what? It's actually x squared plus y squared equals to 2 squared. So it tells you actually these intercepts at the x and y axes are both 2, right? So the circle here is actually the circle centered at the origin, and the radius is 2. Okay? So indeed, this height is exactly the same as this radius right here. So this is exactly a cone. So now let's see. We want the volume that's enclosed by this lower bounding paraboloid, and we have on the top, this is the cone that's covering the upper half of it. Okay. So somehow we want to know at which point they will intersect. Okay. So if we put this figure together, so basically on the top, we know there's a cone, right? But at the bottom, this is a paraboloid. So the top cone. So they intersect at a certain circle, right? And then at the bottom, you just have that paraboloid. And so basically, we are keeping the lower half of the paraboloid. So essentially, the axes are there at the bottom. So x, y. Okay. So although we don't really know where the intersection is, but we know the figure somehow will look like this. Okay. So this is the z-intercept 2. Okay. So this is z equals to 2 minus the square root of x squared plus y squared. And on the bottom, we have z equals to x squared plus y squared. All right. So so that's the illustration. But we here in the just recall this question wants us to find the volume of the solid that's enclosed by these surfaces, right? Lower bounded by the paraboloid, upper bounded by the cone. Okay. So here it's very important to get the intersection. Okay. And of course, when you do the intersection, you just want to make sure that the the z value of the upper bounding surface equals to the z value of the lower bounding surface. Okay, it's making the two equations satisfied at the same time. So getting rid of the z, you will have what? You have x squared plus y squared equals to the functional value of the other cone. Okay. So actually, you have a if you look at this, this is actually a quadratic equation in terms of the radical. Okay, so this is something we need to solve in order to get the intersection. Okay? So once we solve for this, we will be able to identify the projection of this circle on the xy plane. Okay, and once let me make it a bit larger. So essentially, we want to describe the solid over the region that's exactly above this D. And that's the region B. Okay. So once we get this intersection, we'll be able to know the solid is defined on what region, right? So let's put the things down. Note that on the intersection of the surfaces, we know that the functional value of the paraboloid must equal to the functional value of the cone. Okay. So like we mentioned, x squared plus y squared is actually the square of the radical. Okay. So we can treat that radical as you can say as a variable. Okay, although it looks complicated. But then we move the radical from the left hand side to the right hand side, excuse me, from the right hand side to the left hand side, and also subtract the 2. So this is exactly a quadratic equation, right? So basically, if you see this as kappa A, this is kappa A squared plus kappa A minus 2. Okay, so this quadratic equation helps you to solve this kappa A. And then here you can do some factorization. Okay, so here we just omit the details. That's something you probably are very familiar with. So if you factor, you will have that cap A plus 2 times cap A minus 1, right? And of course, this one will not really help you because this is always positive, okay? So you will only get the solution that the radical has to be equal to 1. This part is always positive. So so this tells you that cap A, this radical, must be 1. Or in other words, we are intersecting on the unit circle. Okay. So back to the picture right on the top. So basically, it tells you what? It tells you if you are doing the cross sections when you fix the z values, the biggest cross section cross secting circle is exactly the unit circle. Okay. And then if you have different z values, the cross sections will be circles that are smaller, right? Will be something like this, or something like this, on the cone or on the paraboloid. But the circles will be smaller, right? So this tells you if you do the projection down to the xy plane, you will get that disk cap D, right? So then we calculate the volume. So the region cap D equals to the xy pair such that x squared plus y squared is less equal to 1. And the volume we can describe as the double integral over this region D. And it's so the height here is actually the upper bounding surface minus the lower bounding surface, right? So this is the cone minus the paraboloid. Okay. So this is one of the properties that we have to calculate the volume of a solid, right? But here the only difference is that we have a D with the general region. This is still one of the properties from the previous section. Okay. But here we just want to remind you guys that this is going to be not easy if you deal with it using the xy coordinates. So let's quickly write it down. So using dx dy, then the integral may be complicated. So if you were doing the dx dy setup, then somehow you need to describe this double integral in terms of xy. So here, of course, we know to describe this disk with a unit disk, you know that y has to come between -1 and 1, x is between radicals in terms of the radicals in terms of y. X to y, and then the functional expression is the same thing. So I can achieve by copying this down. Which is definitely not simple to calculate. Okay. So in this section, of course, the easier way to deal with it is using the polar because once again, the square root of x squared plus y squared essentially becomes the radius r, right? Because this is exactly the distance from the point to the origin, right? And then this becomes r squared, and then within the bounds for polar coordinates, this is exactly a polar rectangle. Okay, so we have fixed a constant r and theta bounds. Okay, that's something much easier than EXCY. So here using RDR d theta setup. So we know that so let's put so here theta is on the outside, right? So theta is between 0 and 2 pi. R is between 0 and 1. Right? R dr d theta. We keep it there. And then here, the only thing that we need to worry about is the substitution for the functional expression. So like we mentioned, the square root of x squared plus y squared is exactly r, right? So this is 2 minus r minus r squared. So here, instead of directly writing r, let me write one more step. So basically, this is the square root of r squared, which of course equals r, since our radius is between 0 and 1. Okay. So we use the fact that x squared plus y squared is replaced via r squared. Okay. So this is the way that we get rid of the variable within the expression. Okay. So finding questions. So this is the key step that we translate everything comes about from xy to r theta, right? And as long as we have a sum of squares, it will simplify to something about r only. Right. That's good. And the rest is just calculation. Okay. So here we see this is just the level integral where we have theta between 0 and 2 pi, r between 0 and 1. But now, so if you look at the function here, in the square brackets, you have a function in terms of r only, and then on the outside you're multiplying by another r, right? So we can distribute this multiplication. So this gives you what? This gives you a polynomial inside, which is 2r minus. So the circle part is r, right? Multiplying by the outside r is going to be r squared. Finally, we minus r squared times r, which is r cubed. Okay. And now further, we notice that, okay, since the function is only about r, so this inner integral will get you a constant value. Okay, so so you integrate the function only about r, that's going to give you a constant. And then on the outside, you have an integral in terms of a constant with respect to theta. Right, so this is exactly 2 pi multiplying by the integral that you have on the inner part. Okay. And then, so with some calculations that are not hard to check, this is just a integral of a polynomial, right? So you should get 5 pi over 6. That's the kind of answer. Okay, so this example actually concludes the section of double integrals over using polar coordinates. So here I just want to quickly mention that we just did an example using. So you see these are this is a polar rectangle, okay? Earlier we also have the region that's described by having functional bounds instead of constant bounds, okay, for something on the inner. So that's just like a quick extension for more general polar regions. So if you want to look at more examples, you can look at certain examples from the textbook. But here we're just gonna jump into triple integrals. Okay. So later we will see more examples in terms of cylindrical and spherical coordinates. Okay.